You know, we walk on it, we drive on it, we build these incredible lives on a world that we just assume is solid. But what if it's not? See, underneath all the concrete and steel, there's this complex, hidden science that literally keeps our entire world from sinking. Today, we're going to dig into the ground beneath our feet and uncover the engineering that makes it all possible. I mean, look at a skyscraper. You see the steel, you see the glass. You look at a bridge, you see the massive cables and the concrete. But you know what? The most critical part of all these structures is the one part you can't even see, the ground they stand on. And what holds them up is way, way more complicated than just dirt. So let's get a closer look. To most of us, yeah, it's just dirt. But if you're a geotechnical engineer, that's a specialist who analyzes the earth to make sure buildings don't collapse or dams don't burst, the ground is this incredibly complex material. It's something with properties you can actually measure, predict, and even design for. To an engineer, the ground isn't just dirt, it's a three-phase system. And that right there, that's the fundamental shift in thinking. It's what turns a simple patch of earth into a predictable, buildable foundation. And here it is, the core idea, straight out of the engineering textbooks. Soil isn't just one thing, it's a system made of three distinct parts. First, you've got the solid particles, the sand, the clay, the gritty bits. Then you have water, which fills in the little gaps between those particles. And finally, you've got air, filling whatever space is left over. So, what does this three-phase system actually mean in the real world? Well, it turns out that the precise mix of these three ingredients, the solids, the water, and the air, is what determines everything. It decides whether a piece of land can safely support a small family home or a 100-story skyscraper. Okay, think of it like this. Imagine you have a glass jar, and you fill it up with marbles. Those marbles, they're the soil solids, the actual mineral grains. All that empty space between them is what engineers call voids. Now, you can pour water into that jar, right? It'll fill up some or maybe all of those voids. That's your liquid phase. And any little bit of space not filled with water, well, that's filled with air, the gas phase. Solids, water, and air. That's it. That's soil. So here's the real key. It's not just that these three things are there, it's the ratio between them that dictates everything. The soil's strength, its weight, its stability. And to get a handle on that ratio, engineers use a few key measurements. First up is something called the void ratio. It's a really simple but powerful number. It just tells you how much empty space, the voids, there is compared to the amount of solid stuff. So a high void ratio means lots of empty space, kind of like our jar of marbles. A low void ratio is more like a jar of sand, much, much less empty space in there. Now, there's a similar concept called porosity. It sounds almost the same, but there's a small difference. While void ratio compares the empty space to just the solid particles, porosity compares that same empty space to the total volume of everything, solids, water, and air combined. They're basically just two different ways for engineers to get a number on the emptiness of the soil, which, it turns out, is absolutely crucial for figuring out its strength. And finally, we've got the degree of saturation. This one answers a really important question. Of all the empty space you have, how much of it is actually filled with water? If the saturation is 0%, the soil is bone dry. If it's 100%, it's totally waterlogged, fully saturated with no air left at all. And this number is incredibly important for understanding how that soil is going to behave when you put a massive building on top of it. Okay, so we've got all these technical sounding ratios, void ratio, porosity, saturation. But why does any of this actually matter? Well, let's connect these tiny, microscopic numbers to the massive, real-world consequences they can have. This comparison really says it all. On the left, you've got loose soil. It has a high void ratio, meaning lots of empty space. This creates a really weak internal structure, which makes it prone to something called settlement, which is just a polite engineering term for sinking. But on the right, you've got dense soil. Its particles are packed super tightly together, creating a much stronger, much more stable foundation. And you can see that direct link right here. A high void ratio in loose soil means a really high potential for settlement. That's the engineer's nightmare. A building slowly sinking into the ground because the earth beneath it just can't handle the weight. It's literally why the Tower of Pisa leans. A low void ratio, on the other hand, means a stable foundation. That is always the goal. So this all leads to a very, very practical question.
If we show up at a construction site and the tests show the soil is too loose, too weak, that it has a dangerously high void ratio, can we actually do anything about it? I mean, can we engineer the earth itself?
So can we fix weak soil? The answer is a huge, resounding yes. We can absolutely engineer the earth itself, and one of the most powerful ways we do it is through a process called soil compaction. At its core, soil compaction is pretty simple. It's just the process of increasing the soil's density, making it heavier and tighter. And here's the trick. It works by reducing the volume of air in those voids. You're literally squeezing the air out to force the solid particles closer together into a stronger, more interlocked arrangement. And the transformation is, well, it's dramatic. Look at this. Before compaction, you have a high void ratio, low density, and weak soil. After compaction, it's the complete opposite. The void ratio is low, the density is high, and the soil is strong. The risk of that building sinking is minimized. You've essentially engineered a brand new, much better foundation to build on. And this isn't some abstract idea. It's done with massive, specialized machinery. Engineers use things like giant smooth wheel rollers or pneumatic rubber-tired rollers that use pressure and a sort of kneading action. There are even these things called sheep's foot rollers that have these big knobs all over them to compact clay soils from the bottom up. The machine you use all depends on the specific type of soil you're working with. And this really gets to the heart of it all. Geotechnical engineering isn't just about passively looking at the ground and taking notes. It's an active, incredibly powerful discipline that literally reshapes the earth. It's about transforming weak, unreliable soil into a foundation strong enough to build our entire world on. So we've seen how a deep understanding of something as simple as dirt allows us to build a safer, more ambitious world. It really makes you wonder, doesn't it? What other invisible forces that we all take for granted are just waiting out there to be understood, to be quantified, and maybe to be reshaped for the better? Thanks for tuning in.